interesting thing that we've observed over eons of human experience, any object dropped near the surface of the Earth falls with constant acceleration in the absence of air resistance. Free fall acceleration works as long as we are in the lower portion of the atmosphere. We are not going to get outside of that in any of our problems. If you are going into astrophysics, if you are going to do stuff where you're talking about objects moving in the upper layers of the atmosphere, if you are going to talk about stuff that's leaving the atmosphere, you do have to account for some variation there. But at the locations that we're going to talk about, we can assume constant acceleration. That constant acceleration is known as g, lowercase g. And it is 9.81 meters per second squared. Hey, if you figured out the slope of your velocity timeline, what do you think it should be close to? Yeah, if you did a velocity time graph for your object and you got a slope of 10, you're a rock star. If you can get a slope of 10 with the kind of primitive instrumentation that we're using and the primitive observation that we're using, you're doing really well. G is towards the center of the Earth. So by convention, we show down as negative. We say that the acceleration of objects in free fall is negative g, or negative 9.81 meters per second squared. Somebody forgot to put their units in there. Oops. I'll fire my note writer. So you can throw an object up. Once it leaves your hand, it is in free fall because there's no longer any force other than gravity acting on it. It is free fall. So the question is, what if I chuck that thing? What if I stand on the balcony and instead of just going, oh, let it go, I go, woof, because I'm having a bad day. Is that still free fall? Yes. Because once it leaves your hand, even if you gave it initial velocity, once it leaves your hand, there's no force acting on it other than gravity. So it doesn't have a zero initial velocity. It has an initial velocity because you threw it, but it's still now only got the force of gravity acting on it. Good question. And this is one that, for whatever reason, is challenging. When the only force causing the acceleration is gravity, acceleration equals 9.81 meters per second squared down, period. And we'll get to why that, I don't have a negative in there in a little bit. We toss a ball up into the air. I think you've done this recently. Toss things into the air, perhaps. As it's rising, it is accelerating at 9.81 meters per second downward. There's a moment at the top, we often call it top of flight, where it stops for a moment, and then it reverses course and it plummets back to Earth. In that moment where it has no velocity, what's its acceleration? 9.81 meters per second down. As it falls back down to Earth before crashing with a thud, what's its acceleration? 9.81 meters per second down. Whoops, I forgot to record all that. So until they pull their chute, they are accelerating at g. This ball, even though it's being thrown up, is accelerating at 9.81 meters per second downward. Now remember we talked about positive and negative acceleration and speeding up and slowing down and your head hurt a little bit? This thing is traveling upward, but it has negative acceleration. What's happening to its velocity? It's slowing down. And this is consistent with your observations over a lifetime of throwing things up into the air. If it's traveling under the influence of gravity, it is accelerating at 9.81 meters per second downward. It's not tricky, but you have to be careful. You have to be very, very aware of this. We have used sine as a proxy for direction on the x-axis. What we're doing here is just turning everything 90 degrees. So we've gone from the x-axis to the y-axis for our motion. On the x-axis, I had people saying things like, negative distance doesn't make any sense. I know. It makes a lot more sense to most people on the y-axis. Because if something starts off, I don't want to drop that. If something starts off, oh, here we go, I can drop this. Here, what, like 1.6, 1.7 meters above the ground? This is positive 1.7 meters above the ground. If there's a hole cut through my floor down into Mrs. Berger's room, and we're calling my floor 0, if this thing goes all the way through, it's going to have negative distance. It's going to be below 0. It makes a lot more sense on the y-axis for most people. By convention, we do call anything traveling up away from the surface of the Earth, up into the atmosphere, up into the sky positive. Anything traveling towards the Earth or towards the center of the Earth, really, because that's where gravitational force originates from, we call negative by convention. So, with that, to do this. So G, it's got that magnitude, 9.81 meters per second, and it is generally used in the negative 9.81 meters per second squared, because acceleration due to gravity is heading towards the center of the Earth, and therefore, heading towards the center of the Earth, it's negative. So let's do the sample problem. Jason hits a volleyball so it moves upward with an initial velocity of 6.0 meters per second straight up. If the volleyball starts 2 meters above the floor, how long will it be in the air before it strikes the floor? Assume Jason is the last player to touch the ball before it hits the floor. So in other words, what we're describing is an object that travels upwards with some velocity. We know from experience that it's going to get to some point where it's going to stop, it's going to turn around, it's going to start plummeting back towards Earth. And what we want to know is the amount of time it takes to do this. So what do we have? Well, here's what we have. We know that it started out 2.0 meters above our arbitrary 0, which is the floor. So what is its displacement? Talk at your table. Don't yell it out. Talk at your table. What's its displacement from its initial position to its final position? And this is delta y. Why is it negative 2 meters? Because its final position is 0 and its initial position is 2. Final position minus initial position, 0 minus 2 gets you negative 2. That matters a lot. That matters a ton. So delta y is negative 2.0 meters. Please, 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 please don't be that one. I had one person many years ago who said, yeah, you know, I don't really like using y. I'm just going to use x. No, don't do it. This is the y-axis. Use y. Because in the next chapter, guess what we do? We do motion on 2 axes, and you have an x displacement and a y displacement. And if you're calling everything x, you will die a sad, painful, brain-exploding physics death. They eventually got over it. So we have a displacement. We would like time. Okay. What else do we have? Oh, we have acceleration. And actually, it's just acceleration because it's constant. So it's initial, it's final, it's everything. What is it? Negative g. Negative 9.81 meters per second squared. We've got one other thing. We have VI. We're told that it's hit upward with an initial velocity of 6.0 meters per second. Now, you got your handy-dandy note card ready, right? You have an equation that connects delta y or delta x displacement with time, acceleration, and velocity. You do! My favorite for no rational reason whatsoever. Yeah.
We also have our final velocity.
No, it's not. Nope. Because at the point when the velocity goes to 0, that is because a force has acted on it. That force is the floor. So our final velocity under the influence of gravity is not, in fact, 0. If you cut a big hole in the floor, this thing would continue to accelerate. So we can't use a final velocity of 0 because it has a non-zero velocity in the moment before another force acts on it. But People always try that. That's a pretty common path, and it's a really dangerous dead end. It will get you a very incorrect answer. There comes a point in every physics student's life when we have to stop and talk about the quadratic equation. Today's the day, kids. You knew it would have to come. If we wanted to use this equation to solve this problem, we would have to plug it into the quadratic equation, because we are solving for a variable which exists in both just delta t form and delta t squared form. We can't solve that without the quadratic equation. I'm going to make a confession. I love math. I would do algebra recreationally. Like baby calc is also pretty recreational. It's fun. It's easy. I like it. I could move those numbers around all day. I hate the quadratic equation. There, I said it. So we have an alternative pathway, and if you are one of my like super math geeks, years ago I had a student who, after I did my little like end run around the quadratic, which your book uses too, I just realized, she came up to me and said, "Did you realize that when you do this whole end run and you rearrange it, what you get is essentially the quadratic equation?" That's fine. So if we aren't going to use this, is there something else we can use that would connect VI and displacement and acceleration? Well, what if we did find the VF in the moment before it hits the ground and the ground stops it? What would that look like? We don't have that either. So we could do this. VF squared equals VI squared plus 2a delta y. We could find what its final velocity is in the moment when it has gone negative 2 meters from its starting position. So VF would equal the square root of VI squared plus 2a delta y. Or there are two ways to tackle this. We could just solve for VF. And once we've solved for VF, if we have VF, well then we could use VF equals VI plus a delta t. That would be easy. That would account for our acceleration. It would use only things we've got. To solve for delta t, we could then do VF minus VI divided by a equals delta t. That's pretty straightforward. The thing that you're going to have to get used to and good at is substitutions. And this is where everybody kind of balks. And what I'm going to tell you is that you should become comfortable doing the substitution and writing it that way and doing the algebra, because there will come points where you can't just calculate one thing and plug it back in. You need to do multiple substitutions. So what would that look like? Well, that would look like taking this and sticking it there. And it does make the algebra a little ugly for a moment. I'm not going to be disingenuous with you. There's no way around that. But let's go ahead and actually do that. So we get the square root of VI squared plus 2a delta y. And I'm going to put that in parentheses because it helps to separate it out. Minus VI all over acceleration equals delta t. And this is where this, I think it was here, the student came to me and said, "Do you realize that that's almost exactly the quadratic?" No, I didn't realize that, but thanks. So at this point, because I hate the quadratic, at this point we can go ahead and plug in. We've got everything we need. And again, you can walk through and solve for VF first, but it's cleaner and more elegant to do this all in one step. So let's plug in. So if we plug everything into that, we get square root of 6.0 meters per second, quantity squared, plus 2 times negative 9.81 meters per second. Oops. Okay, so we have plus or minus the square root of 6 squared plus 2 times negative 9.81 meters per second squared times negative 2 meters squared. quantity, minus 6, divided by negative 9.81 meters per second squared. Who's got a raw answer? So here's, I'm going to forego the conclusion, because it's in your book. This is a sample problem. The raw answer for time is 1.4958 blah, blah, blah seconds equals delta t. Sig figs out to 1.5, they say 1.50. I think it's just 1.5. Yeah, 1.5 seconds equals delta t. Their sig figs are wrong. So, how can you screw this up? This is the question you should always ask yourself when approaching any complex problem. How could I screw this up? And I'm going to tell you some of the most common ways to screw it up. Disregarding, and this is the single most common thing, this plus or minus the square root has never been more important in your life. Think about the object of this ball. It has risen up into the air, it has stopped, and it is now hurtling back towards the gym floor. Is its velocity positive or negative? Negative, and I can guarantee that's what you did, Vince. It's got a negative velocity. Well, I can't guarantee, but that's my first check item on the list of how could I possibly have screwed this up. That velocity is negative. So the raw answer that we get for that is 8.6740, blah, blah, blah. But it's negative 8.6740, blah, 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 blah. Well, when you take that negative 8.67, etc., and you subtract another 6 meters per second from it, you get negative 14 point something, negative 14.674, blah, 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 blah. Well, now you're dividing that negative 14 by negative 9.81 meters per second squared. The other clue is if you ever get a negative number for time, you need to go back through the whole problem and check all your signs. When we were doing the x-axis, the signs for direction were a little more forgiving. Here, the signs for direction are so much less forgiving, because once you screw up the sign, it very often will change the magnitude of your answer. So it's a good place to be really careful. Did everybody get the raw answer? And that reminds me, because I know that what's under there is standing in for VF, and I know that VF should be negative. So if I write the negative of the square root of all that, that helps me not make that particular mistake. Okay, all of the practice problems for 2F are assigned, and those are on page 65, I believe. When you're ready, I have the 2F worksheet, odds. And I'm thinking we're not going to get a Chapter 2 test in before the 9 weeks ends. It seems unlikely. So you've got the lab going in. You'll have a FIP. Yeah, I don't see how you could have a Chapter 2 test by Friday. Might be able to get one in by Monday. Let me think about that. Let me think about if I can do any fudging. We'll see where you guys are at. There's no rush, lady. It's not a big deal. Why are you racing? So anyway, get working, and we'll talk as we go.